Hello, everyone. Welcome to the third episode of Math-Adda. I'm your host, Shankhadev. As in the two previous episodes, we are going to take an INMO problem as a conversation starter. Let's see the problem first. Okay, so whenever we are given a problem, before we start solving it, we make some general observations. In this particular problem, what should catch your attention immediately is the form of the x. Okay, because this is a very special form. This is not an accident. To me personally, this looks very much like a made-up problem. When you do research problems in real mathematical research, things do not come in such nice sum format uh, with combination symbols and so on. Okay. So whenever you are given such a problem, it is usually an Olympiad problem, and you are actually retracing the steps of someone. Someone already did it. Someone put it in a form that would be difficult for you to understand, could be difficult for you to understand you, and you are just supposed to follow in the footsteps of the person. Okay. So this particular form reminds me of the obviously of the binomial theorem, because it has this binomial coefficients. It has n minus 2k, and it has 3 power k. But there is a slight problem. There are two problems, in fact. I will write down the observations. By the way, observation number one, x is positive. X is in fact greater than 1 because the first term in this sum is actually 1. Uh, it's 2 power n, which is greater than equal to 1. So x is positive and x is actually greater than or equal to 1. Observation number two looks like binomial. In fact, it is 2 power n minus 2k, 3 power k. Instead of writing 3k, if I write root 3 power 2k, then it falls nicely into that format. See? Observation number three, related to the expansion of root 2 plus root 3 power n. That should be obvious because if you expand 2 plus root 3 power n, you will get terms of this form. But there is a slight problem. Here, only the even terms are appearing. So usually you would have n choose 1, n choose 2, n choose 3, you will have everything. But here you have n choose 0, n choose 2, n choose 4, like that. So it is related to the expansion of 2 plus root 3 power n, but it's not exactly that. But this can be easily remedied. What you do is you compare this with the expansions of 2 plus root 3 power n and 2 minus root 3 power n. Now, when you expand this second thing here, second power here, you get things like 2 power n minus 2 power n minus j minus root 3 power j. Now, when j is odd, there is a negative sign in front of this. So if we add these two, all the odd terms are going to be cancelled, and there will be a factor of 2 in front of the even terms. So this actually gives us 2 plus root 3 power n plus 2 minus root 3 power n is equal to 2x, or x is equal to 2 plus root 3 power n plus 2 minus root 3 power n. By the way, x is greater than equal to 1 and x is an integer. X is greater than 1. X is greater than 1 and x is in n. It's a positive integer. Okay, these are the three initial observations we have. They're not immediately useful, but they might be useful later on. Okay, let's continue. Let's get back to the problem. So the statement of the problem is about sides of a triangle. You're given three numbers. You're supposed to show that they form the sides of a triangle. How do you check that? Usually, what we do is we we use the triangle inequalities, right? So if A, B, C are three numbers, we check whether they're positive first. And here as x is a positive integer, all these three are positive. So we do not need to check that right now. Then what we do is we check the triangle inequalities. This is one way to do this. But actually, there is another way. Given the sides of a triangle, there is a formula to find the area of that triangle. And you probably know it. It's called Heron's formula. It goes like this. S is defined to be A plus B plus C by 2. Why S? S stands for the semi-perimeter. A plus B plus C is a perimeter and the half of it is semi-perimeter. And it can be shown that the square of the area is actually S into S minus A into S minus B into S minus C. If this is 0, then the triangle is degenerate. If this is greater than 0, then it is a real triangle. Okay, and you can actually check that if this is greater than 0, then the triangle inequalities that are given here actually hold. By the way, when I say degenerate, it means the triangle actually reduces to a line. If you take a line segment or a line, and if you take 3 points on them and you try to find the area is going to give you 0. Okay? So this is what we are checking. And as this particular problem also talks about the area and the in radius, it makes more sense to talk directly about the area without talking about the triangle inequalities, because we have to find the area anyway, right? So we find the area, check whether it's positive or not, and if it's positive, then we conclude that they indeed form the sides of a triangle. Fine. So let us do the calculation. S is 2x minus 1 plus 2x plus 2x plus 1 by 2, which is 6x by 2, which is 3x. Therefore, s minus a is 3x minus 2x minus 1, 6x minus 1. S minus b is 3x minus 2x, which is x. And s minus c is 3x minus 2x plus 1, which is x. Oh, by the way, this is x plus 1. Sorry. And this is x minus 1. Therefore, delta square is 3x squared times x squared minus 1. We have already commented about the fact that x is greater than 1. So this is clearly greater than 0. And the area is positive. So the three sides actually, the three numbers do form the sides of a triangle. And there's more actually. So x is a positive integer. So 3x squared times x squared minus 1 is also a positive integer. So, oh no, you have to check. You have to check if the root is positive. Fine. Integer area and in radius. So what you need to check is whether delta equal to this is an integer. So you need 3 times x square minus 1 to be uh, to be a perfect square. Let's get to the in radius now. We know that in radius r is given by delta by s. This is a pretty well-known formula. You can derive it on your own. And that is, in this case, so we need to prove that 3 times x square minus 1 is a square, a perfect square, and x square minus 1 by 3 is also a perfect square. Let's focus our attention on the second equation for the time being. Let's call these equations 1 and 2. Note that solving the second equation is equivalent to solving the first equation as well, because if x square minus 1 equal to 3z square, then 3 times that is 9 times z square, which is a perfect square. Okay? So we can forget about the first equation. We will just solve the second one. So we need to solve x squared minus 1 equal to 3z squared, which is the same as x squared minus 3z squared is equal to 1. Now, this happens to be a very famous equation in all of number theory. It's called a Pell equation. Okay? A Pell equation is an equation of the form x squared minus capital D y squared is equal to 1, where D is not square and x and y are positive integers. There is a result saying that this always has a solution. Okay? And in fact, if it has one solution, then it has infinitely many solutions. This is a result that we are not going to see today. And this is a result that you won't find in Olympiad level books usually because it's a bit more involved. It involves concepts from number theory such as continued fractions. By the way, the continued fractions is a concept which was studied extensively by our own Ramanujan. Usually, this is beyond the scope of Olympiads, but as this is a Math-Adda, it does not have any limits. If you want, we can do a more detailed discussion of that in the next episode. So, if you want an episode on the details of Pell equations, let me know in the comment box, and we can do it in the next episode. Okay, next week or the week after that. Fine. And this has a very curious history. This was first studied by Brahmagupta from India. And the ancient Indian mathematicians, not just Brahmagupta, others as well, they already had a solution, they already had a general method for solving many Pell equations. And Europeans had no idea about that. Then later, other people started solving it as well. And the first European to make a significant contribution to this was William Brownker. I don't know if this is how it is pronounced. Okay? Now you must be thinking, why is the equation called Pell equation? Who is this Pell? Now Pell was some other guy who had nothing to do with this equation, and he actually revised one of the translations of Brownker's work. Just that he didn't even do the translation; he just revised the translation. And Euler is considered to be one of the greatest mathematicians of all time. He saw the translation and he mistakenly attributed the work to Pell. And Euler was so influential that just this attribution by him made Pell the owner of this equation for all posterity. Even so many centuries later, we call it Pell's equation, but Pell had nothing to do with it. So such accidents happen in history. So the general idea of solving this is finding a least solution. What does it mean? That means we need to find a solution such that x naught plus y naught root b is the least. We need to find x naught comma y naught such that this quantity is the least. And once we have that, we can generate many solutions from that. How? See, x naught square minus y naught square d is 1. That means x naught plus root d y naught times x naught minus root d y naught is 1. Now we can take nth powers to both sides. And you can check using binomial theorem that this first term is of the form xn plus root d yn for some xn and yn, and the second term is xn minus root d yn for the same xn and yn equal to 1, and that actually gives xn square minus dyn square is equal to 1. So xn and yn is also a solution. It is possible to show that if x naught and y naught, x naught comma y naught is the least solution, then any other solution can be obtained in this way. It's not too hard to show, and if you can show that, please tell me in the comments box, okay, how to do it. Fine. And note that it depends on finding the least solution. This process, finding the least solution. If you can find a least solution, you can find the other solutions. But what is the guarantee that you are going to find a least solution? That's where the general theory comes. What you do is you take root d, you do a continued fraction, and there is a way to find a least solution using that continued fraction. If you're interested, I can do it, we can do it in the next session. But usually, in the problems we encounter, the least solution is very easy to find. For example, in this one, it is clearly 2, 1. Because 2 square minus 3 times 1 square is equal to 1. Therefore, any other solution xn comma yn must, actually this is z, xn comma zn must satisfy xn plus zn root 3 is equal to 2 plus root 3 power n, and xn minus zn root 3 is 2 minus root 3 power n. Summing them, we get 2xn is equal to 2 plus root 3 power n plus 2 minus root 3 power n, and that gives us xn equal to 2 plus root 3 power n plus 2 minus root 3 power n by 2. Does this remind you of something? This is precisely x. Now you see why our observation is useful. As we already know that this is x, we know that for x, this second equation, this one here, it holds. As the second equation holds, the first one also holds. So both the area and the in radius are integers. Thus, this problem is solved. Okay, actually, it was not necessary to touch upon Pell equations for to solve this problem, because you could have, as you actually have x equal to this thing, x equal to 2 plus root 3 power n plus 2 minus root 3 power n by 2. You could have plugged that in directly here, and you could have checked by hand that it is actually satisfied. But talking about Pell equations is much better, right? So if you want more about Pell equations, please let me know. We'll talk about in the next episode. See you later. Bye-bye.